Now, so far we have derived that how the expectation value of the position changes with time, and we have derived equation 9. Now we are going to find out how the expectation value of momentum, that is P expectation, that changes with time. That is, we need to find out ddt of expectation value of P. For that, we first need this commutation relation between the Hamiltonian and the momentum itself. Now, Hamiltonian contains two terms. So one is p square by 2m, which is kinetic energy term, and other is potential energy term Vx, that is the particle is subjected to this one dimensional potential which is called Vx. Now P always commutes with all of its functions, so this term will be 0. We are remaining, we have this term only. So now we need to find out this relation. I have just switch the order, so the minus sign appears here. And we know that commutation relation of xp will give me I h cross, and this is a function of x. Now I am going to show you a relation which I have derived, because we are going to use that here. Now the relation is a b to the power n. Now this b is any polynomial. B to the power n is just any polynomial of b, like it's a function of b operator, and this commutation relation will be this one. If ab, the commutation relation of ab is I alpha, then we have this, and I have proved this using this commutation relation of AB equal to I alpha that is given. I have proved this equation. This I have shown already, that A B square gives me 2I alpha B. Now here instead of n I have put k. K could be anything like 5, 10 or maybe 100, anything. So this is basically a commutation relation of A and the polynomial of B, and this will be like this. And now for n equal to k plus 1, I am just doing this. This is a very simple thing, because a b k to the power a b to the power k plus 1, I'm sorry, is equal to a b k dot b. And now I can write this, from this I can write this, and using AB equal to I alpha, I can write I alpha BK, and using this one, this A B to the power K is equal to K B to the power K minus 1 I alpha, which is equal to this one. So here I have obtained this relation. This is called method of induction, because for b to the power 1 this relation is valid. For b to the power 2 it is just the 2 factor comes here, I alpha remains the same, and I have this b operator. For k, that is if it is b to the power k, so I obtain this. Now if it is for b to the power k plus 1, so I have obtained this. So the method of induction tells me that as it is valid for n equal to k plus 1, so for b to the power n the same relation will be obtained. And this is another identity I have shown, because this type of proofs you may get in your examination, or maybe in doing some quantum mechanical problem you may need this type of commutation relation. So I have additionally derived this also. So using this thing, that the commutation relation of A operator and the function of B operator, now this function is polynomial of B, gives me this one, because n b to the power n minus 1 is something like making derivative of this B operator, because we know if we do ddx of x square, we will get 2 into x to the power 2 minus 1. So this thing, this n b to the power n minus 1, this is nothing but the derivative of this b operator. So using this relation, I have obtained equation 10. So the commutation relation of the Hamiltonian with the momentum operator is basically IH cross dV dx, and we have previously had this relation, this equation 3, which tells me how this expectation value of P changes with time, and this was this thing, the right hand side I have already obtained. The commutation relation of H and P is obtained as IH cross dV dx. So I am going to use equation 3 and equation 10 to obtain this relation, this equation 11. And this is a very important in terms of physics, in terms of understanding the quantum mechanics. Here we have obtained a relation which is almost equivalent to the classical mechanics, because we have just thrown out this H cross. This H cross is completely disappeared in equation 11. So this means that if a particle is subjected to the potential Vx, then the center of the wave packet just moves like a classical particle, because dp dt is nothing but the force, and we know that for a conservative force field, force is equal to negative of the derivative of the potential. So this Ehrenfest theorem is quantum mechanical analog of Newton's second law, and this theorem was derived by P. Ehrenfest in 1927 using the formalisms of wave mechanics. So now we can see that both sides we have expectation values. So classical mechanical results are still valid in quantum mechanics at the level of expectation values. Now we would like to discuss two pictures. One is Schrödinger picture, other is Heisenberg picture. In Schrödinger picture, the state states, the state vectors, they vary with time. And in Heisenberg picture, the operators vary in time. But we will readily show that the expectation value remains the same for both Schrödinger and Heisenberg picture, because expectation value is the same, which is of a physical importance. So that should not depend on the picture we use to derive them. Schrödinger equation is the basic equation of Schrödinger pictures, in which these state vectors, the state states psi, are varying with time.